we'll start with the three-phase systems. All right. So when we consider the electrical energy flow, and whenever we want to uh, convert the electrical energy to other forms of energy, right? Other forms of energy, basically electrical and the mechanical forms of energies are very widely used. And why I say very widely used, because they are there is a most necessity of conversion of electrical energy into mechanical energy, or vice versa, because power generation, power conversion, etc., are going to be dealt in the same fashion. So let's say, if at all you want to do this kind of conversion, right, there is one very important aspect or one important domain that comes into picture. All right. So if you want to talk about that, right, why I'm talking that, because that's one of the very important aspect. Why do you need to study these AC circuits, three-phase AC circuits, etc.? Okay, just to justify that, I will try to draw one very simple diagram. All right. So this is a domain which is very important whenever the electrical energy conversion or the power conversion happens from electrical to others, or electrical to electrical itself. That is actually is what is called as the magnetic domain. All right. The magnetic, there is in some format, either you will see magnetism coming into picture, or you will also see the magnetic field coming into picture, or in some sort you will see a magnetic domain coming into picture. Okay, so this happens whenever you have either this conversion, right? Input is electric. I can write, I'll write electrical, or maybe the output is electrical, let's say. All right, electrical energy is given as input, and you take out the electrical, right, energy as output. This is one possibility, right? The other possibility could be your input is actually, in the sense, you are taking the input energy in the form of mechanical, right? And you will take out the energy, right? Anything is possible. You give input, your input is mechanical, take out electrical. Input is electrical, take out mechanical, right? Both are fine for us. Right. Now this happens. In order to achieve this, there is one more very important concept, right? That actually bundles up, that actually tries to uh, uh, connect every part that we have drawn here, right? So I'd like to uh, add it in this form. Okay, so this domain is fine for us, but what happens here, the electricity should be in the form of AC only, it's not in DC. All right, the power conversion normally electrical to electrical, or electrical to mechanical, mechanical to uh, other form of mechanical, anything you try to do here, right, always happens in the uh, alternative current. Okay, it's a AC quantity, right? Since you already have an idea about what AC is, right? So everything you studied over there is applicable for this purpose, right? Now let's move ahead. Now, what happens if you have a single power supply, AC power supply? Let me try to draw a very simple circuit to start with, right? So you know that how the AC circuit is represented. There is a power supply, and you can have something called as a load, right? So you will write plus minus. Normally, small letters are used for the representation of AC quantities. AC voltage is V, small letter. The AC current flowing here is small letter I, and the voltage across, there is some voltage drop that's going to come across this load, and you denote that as, say, Z. All right. So this Z can be made up of, you can have pure resistors, resistance along with capacitance, resistance along with inductance, or a combination of resistance, inductance, capacitance. All these are possible over here, right? So if this is a representation and you try to represent this voltage in many formats are possible. So one of the very famous one is a phasor representation, right? So you give a magnitude and some angle. So any AC quantity, I'll come to the phasor. Okay, I'll touch the phasor as well, right? Initially, let's look at the basics that are required. I'll come back to the phasor once. Okay, sure. So any AC quantity, basically we expect there are many forms in which you can write, but the most preferred one in the industry, as well as whenever you do some calculations, or it is easy to enter even in the calculator, is called as the phase angle notation, right? So you will write a magnitude, something called as R angle theta, correct? So this is the phase, correct? This is called as a phasor, polar format. There is a magnitude and a phase associated with that. All right. So if at all you try to represent right in this format, that's the most preferred format of AC quantity. Okay, right. So always the research was being taken care in such a way that how do you reduce the overall cost of a power delivery system, basically, for which you let us try to begin the whole concept with what is called as a six wired system, right? So this is called as a six wire system. So what the six wire system comes into picture because of this system. You can see that what circuit we have written here, right? It is a two wire system. Where are the two wires? One wire which takes your current from the source to the load, and another wire takes the same current back from the load to the source, correct? So there are two wires like this, right? Let us consider, because we are coming to the three phase system. Why the three phase is necessary? In order to understand that, we need first to consider a six wire system. So that has no meaning, no significance, basically. But in order to understand why do you need a three phase, what is the advantage of three phase, etc., we definitely need we need to consider a six wire system. All right. So six wire system is basically a AC. It's a AC system. Okay. So let me consider three power sources. I'll draw three power sources over here. This is power source number 2 and power source number 3. So I understand that since I'm actually interested in a six wire system, I need to consider three power sources, and I need let us say three loads. This is load number 1. I need a load number 2, and I'll consider load number 3. Okay, there are three loads. Let's make the connection. So from here, right, I'll take the connection like this, and I'll connect this to the first load, and I need similar connection to carry the signal back, right? So that's the system number 1. All right, same thing we'll do with others as well. So we'll take up, okay, so this carries the signal from the second source to the second load, and I'll do the same thing. From the second load, I connect another wire which actually takes this from the load back to the source, right? And we'll do the same thing here. All right, so this is how a six-wire system looks like. Let me give the names of various quantities that we are looking for here, so that we can use the same quantity names even at a later stage. All right. So uh, let me call this as change the color. So this is A. This is a point A. This is a point B. This is a point C. All right. So there is a current that flows here. I'll call it as IA. Another current flowing here. This is IB, and this is the current IC. All right. So let's assume that there are equal amount of resistances connected over there, and we have AC power supplies denoted like this, right? So uh, I'll write this is plus minus. Initial the polarity will be okay. Let me try to write the neutral point here. This is N1, this is N2, this is N3, because there are three different, the circuits are not connected, right? So whatever circuits we have connected here, they are not internally connected. So neutral lines are different. N1, N2, N3, I can definitely write. So this is E, A, N1, the voltage, EMF between A and N1. So I'll write another name here. This is plus minus E, this is B, N2, plus minus EMF between C and 3. All right. So very simple circuit. Now so I simply have three different circuits. That's all. Okay. Some power supply for each of the circuit, and some resistances have been connected as a load. Right. So it's a very straightforward circuit. Let me try to write what is the requirement of a six-wire system. If you want to build a six-wire system, very old technique in electrical circuit analysis, right? So if you want to build a six-wire system, people proposed three different conditions, right? It's anyway, now we are not going to use it, but uh, to understand, right, how it was built and how it led to the concepts of three phase, this is important. So it's the point number one. The condition is that the peak amplitudes, six wire system. All right, not, we didn't reach the three phase yet, right? I'll come to the three phase. Let's understand what is this. We'll use the same conditions to come to the three phase ultimately. All right, six wire system, no phase. Don't, no phase yet, right? There is no question of phase in the six wire system, right? The peak, point number one is the peak amplitudes of all the three waveforms, right? I'll just write their names itself. EAN1, comma, E, not A, sorry. Second one is B. All right, B, N2, and ECN3. This peak amplitudes of each of them are, right, or should be, you can write same, right? You mean if I draw like this first waveform, this peak value is there, right? The peak value of this should be same as all the three. All the three should have the same values, right? One is 10 volts, other one also should be 10 volts. Each three of them should be having the same thing. Okay, so that's the first thing. Then now we'll come to the second point. The point number two is about the phase, right? So this is E, AN1, comma E, B, BN2, and E, CN3 should have a 120-degree phase shift. Phase shift with respect to each other. Okay, I'll explain you what is a phase and what's a phase difference. All right. So, but before that, if at all I want to write a phasor diagram, right? Let's start from how do you generate a phasor diagram first. So, if you know how to generate a phasor diagram, and that phasor diagram will help you in identifying the phase. Okay, so that we'll understand phase and phase difference altogether. Okay, so what I try to do now, let me try to consider a simple waveform. Okay, this whatever I am writing now has nothing to do with our three-phase system. It is a general phase and phase difference. Okay, I'm trying to answer that. So what I'll do, I'll draw. Let me try to draw. Say, I'll try to draw something, and this part. Okay, all right. So what I do here in this graph, I'm going to plot a simple thing. So as I know, this will be the time and this will be the magnitude. Let's say I'm plotting a voltage waveform. The voltage waveform looks like this. Okay. And on the other side, what I try to do here, this is the concept that actually relates our everything that we are going to discuss now to the phasors. Okay. So phasors are the vector notations for the voltages and the currents. Okay, so consider that you have a circle. All right, so you have a circle, right? So circle, the maximum, the radius is equal to your peak amplitude. Correct. So you see here, from here to here, it's the same. These two arrow marks, whatever I am writing, it's the same. It's the same thing holds good even for this and this. Okay, so that's one requirement. I'll try to draw in the form of this. So the peak values is represented by, sorry, can you repeat the question please? No, circle is the one which I try to use a phasor. I try to bring the phasor concepts inside the circle, right? I try to draw the some arrow marks, some vectors inside this circle, right? I want to restrict the what you call the length of each of the vector same. So just to restrict that, I have plotted a circle here so that I will not cross. In the sense, you see here, I draw a vector here. The maximum, the length of the vector should remain same is my point. So just to make sure that I'm holding to that concept, I have drawn a circle. It's not necessary. You don't have to draw a circle. Okay. So I'm drawing a circle just to restrict myself. I don't want to draw one like this and other one like this. So I want all the lengths should be same. That's all. Okay, fine. Now you see here what happened. Let's say that this is one voltage waveform which I have considered. So look at that, where it starts. It actually starts from 0, correct? Time t is equal to 0. Or if you want to, you can even write omega t here, correct? When you write omega t as axis, you get 0 degrees. The peak happens at 90 degrees, that is pi by 2 or 90 degree. So this happens at pi, right? This happens at 3 pi by 2, correct? And once again, you come back to 0 at 2 pi and so on, correct? So you are aware of this, right? You can try to write, even if you want, you can write in degrees, right? This is 90 degrees, this is 180 degrees, 270 degrees, and 360 degrees, and so on, correct? So 0 is 0 degree. You can draw. So I have a maximum value here and negative maximum over here, right? Could be anything, right? It can be some maximum value, that's all right. Okay, now you see, anyway, my horizontal axis that is plotted along on this graph, horizontal axis, let me consider that as omega t itself. Okay, I'll remove the time. I'll bring back the omega t itself because it becomes easy for you to understand. So I don't want any confusions there. I'll bring omega t here. Okay, so this axis is omega t now. Omega t means its angle. Okay, if you see, if you put t over there, it becomes time. I want to show you in terms of angle, so I'll shift back. Okay, I'll keep omega t as my axis. That's why, so this is justified now. 0 pi by 2 pi, 3 pi by 2 3, etc. are pretty much valid now. Okay, Now you see, think that, right? Think it's something like I have, anyway, I'm starting with 0. So directly I'll mark one arrow in horizontal direction saying that the angle made is 0 degrees. Okay, 0 degrees where, so the convention, again you have a convention coming into picture. If you have x and y axis with you, okay, and I have some line, the angle made with respect to x axis itself is what always considered. Okay, are you okay? So angle made with respect to x axis itself is always considered, right? So this is the positive angle, and whenever I say some angle made with respect to, right, a x axis, y axis, something is considered, means it is always with respect to the x axis. Okay, so now you see, I say angle made is 0 degrees, means it is horizontal. Are you okay? Because that itself is x axis, right? Okay, now you see, you keep rotating this, right? You keep rotating this. Consider that there is a hand. It can be the minute hand of the clock, right? Think that you are rotating at different intervals of time. You reach different points, correct? Okay, I'm rotating this. I'm rotating this at, so start with 0 at time t equal to 0. I'm at this point, so I slightly move this. Okay, in after maybe 1 second, I might reach somewhere here. Okay, after 2 seconds, I might reach here. After 3 seconds, I might reach here. Correct. After 4 seconds, after 5 seconds, maybe 6 seconds, right? Maybe 7, 8, 9, and so on, right? I'll try to draw some of the values on it. Okay, so you see, when this reaches here, it actually corresponds to a point over here, right, on my waveform. So when I reach here, it actually corresponds to a point here, and this corresponds to a point over here, right? The maximum. Now you see, maximum says what? Maximum says what is the angle? What is this angle? 90 degrees. You look at this. This is what is phasor. You look at this maximum angle with respect to x-axis. That's still 90 degrees, correct? So instead of writing a waveform like this, right? Instead of writing the complete waveform like this, you can try to represent the same waveform in this format without a circle, only that vector notation. Okay, so that vector notation which you try to write in terms of magnitude and angle, you see magnitude, what is this magnitude? It's some voltage. Okay, so you see, this is the highest value, I'll call it as some v naught. The minimum value I'm going to write minus v naught, let's say. Okay, so this I can try to write as some v naught angle 90 degrees. That means this is the peak value. Okay, whenever I try to write the same v naught at an angle not minus is not required. Minus is automatically, it will bring the minus into picture. Simply you write 270 degrees. V naught angle 270 means it is minus v naught. Okay, etc. So you can actually bring something like this into picture, but I'll come to that. The how do you get the values, etc. I'll try to write it slightly later. Okay, so, oh sorry, just a second, something changed. Oh, okay, so this, you understood the phasor notation, that's all, right? So the arrow mark what I write here, right, at any point of time corresponds to a particular point in on your waveform, correct? So you see here this point, right, which is actually angle is more than 180, sorry, more than 120, that actually corresponds to this point. So the negative what I have plotted here, that actually corresponds to this pi, correct? Because that angle is pi. So come back. So if you draw something like this, you are actually moving to this point. This is the negative peak, right? That actually corresponds to minus v naught. This point is basically this point, and so on, correct? I am able to represent the different points on my graph, right, by using what is called as a vector notation. We call it as a phasor. Okay, initially, right, you started plotting the wave considering some initial position. What is that initial position? Look at this. So the initial position corresponding to this waveform, what I have written here is 0 degrees, correct? I started from 0, isn't it? Are you okay with that? So I initially started with 0 means the phase of that waveform is 0 degrees. Okay, phase of that wave is 0 degree. Now I will show you a different one where the phase is different. Phase is not 0. Let me consider a different color. Okay, I'll start with another waveform which actually starts from 90 degrees. So the yellow, it starts. Okay, so at 0 it starts from this point, correct? Because it's actually beginning from here. Now as the time progresses, it actually moves to this point. So my next point should be somewhere here. Okay, that is, it's going to reach here. All right, the next point, it is going to reach here. So it's going to reach here, and the next point, it is going to reach here. You see that waveform touches 0. So this is the waveform. Sorry, I'll write again. Okay, and when it reaches pi, it has to reach a negative minimum. So this is how it looks like, and this comes to its negative maximum, means this reaches 0. So this is how it looks like, and something like this. Okay, something like this. And so now you see, now we have a phase difference coming into picture. So what is the phase of black colored wave? Black colored wave has a phase equal to 0 degrees. Okay, the red colored graph, what you see here, has a phase equal to how much? 90 degrees, because it started from 90 degrees. Now this, yeah, are you okay with that? The phases, two different phases we have. Now we come to the phase difference, right? I can definitely measure a phase difference between the two waveforms that you see here, right? The phase of, it's a magnitude, that's all. Okay, you can take a magnitude of both the phases, take a difference. It's one is 0, one is 90. So the phase difference is 90 degrees. Between the two waveforms, you can measure what is called as a phase difference. Okay, phase is allocated. Perfect. So whenever you have two different phase angles associated with the two different waves, then only there can be a phase difference coming into picture. Okay, so one starts at some, say 25, the second one starts at 100. So you know how to find the phase difference, that's all. So phase difference equal to 100 minus 20. So there is a right, 100 minus 20, 80-degree phase difference between those two. Anything. So that's why I said it is easier to represent in the form of vectors rather than in any other format. So now you see that this is one waveform, right, starting at some phase phi 1. There is another one. Okay, let me draw here. This starts at something else. So you can definitely find out what is this phase difference. That's all. Okay, right. So that's what is a phase, and the phase difference is all about. Okay, so originally you will measure phases only. For each of the waveform, individual waveform, you will measure a phase. Then take the phases of, you consider all, how many waveforms you have, all the waveforms, you consider the phase. Okay, then take a difference. Okay, so that you get the phase difference of all those waveforms. Between each of the waves, you can try to find out. Is it okay? Right, so that is the phase and the phase difference. Now we need to apply this according to the point that we have written here. Right, for the first point, you leave it. Anyway, there is no concept of a phase. For the point number 2, it says there is a requirement. The requirement is there has to be 120 degrees phase shift between the three waves that you consider. Right, in such case, if at all I want to draw the phasor diagram. So without this outer circle, if you try to draw the phasor, right, if you try to draw those arrow marks, they are called as the phasor diagrams. Okay, Yeah, you will write, you will, the amplitude, amplitude or the length of the vector that you draw there represents the maximum value of that particular wave. Okay, so let me try to consider this. So I will consider, okay, let me try to draw. Therefore I'm writing the phasor diagram corresponding to the point number 2 now, right? Phasor diagram of this is what is expected. So if you have this as a center, one you consider as 0 degrees only. So let me try to write it as EAN1. Now the EAN2 and EAN1, there should be a difference of how much? 120 degrees. So I know that 120 degree should come here, right? Try to draw the length of this same as EAN1 and you will write it as EBN2. And how much is this? This is 120 degrees. Okay, and again it says that between this and the third one, whatever you draw, right, that should also be having the same what do you call, phase difference. So that is ECN3, right? That also should be 120 degrees, and by default, right, this will also become 120 degrees, right, automatically. So this is again in terms of I have drawn in terms of voltages. Can I write it in terms of current? So answer is yes. Okay, so current will also follow the same this thing. So this could be IA, right? This becomes IB, and this becomes the IC. So again, there is 120 degrees here. This is 120 degrees here. This is also 120 degree gap. So you can try to write either in terms of the voltage or the current. So voltage means you are talking about these three quantities. Currents means you are talking about these three quantities. Okay. So relationship, yeah, diagram is same, right? The phasor diagram is same. Again, from the basics of AC circuits, you should remember that if there is no inductance or capacitance in the circuit, right? E and I are in phase. That's why you see EA horizontal. Look at this one. EA is horizontal. That's why the even the current is horizontal, right? So this is just because of that one fact which is there, all right? And correct. So there is a lead or lag coming into picture depending upon whether you have a inductor or a capacitor in the circuit, right? Fine. So this was a point number 2, and now we'll write the point number 3. Point number 3 is the load should be balanced, right? What do you mean by balanced load? Balanced load means it's the same impedance. Okay, same value. Yes, definitely. Okay, sure. Right. So we understood that this is what is a six-wire system. Basically, a six-wire system, it has fundamentally no applications, right? So they try to do some experiments and they try to build something. So it's updation. So they understood something, and when they try to replace the six-wire system by what is called as a four-wire system, it's an updation. Okay, upgradation you can consider. Okay, four wired system, very similar to the previous case, right? I'll copy the same thing and I'll try to paste, and I'll make only one small change in this whole diagram that we have written so far. Okay, so that is, let me try to, okay, so this was a six wire system. I want to convert this into a four wire system anyway. So they are going to remove the three wires that are located over here. Okay, you don't need the three wires over here. Okay, and replace those three wires by a single wire. That was the concept, and that actually makes sense. We'll justify that in a minute. I'll tell you. Just give me 1 minute. Let me finish this. Okay. So this is what was the next phase in the development of the whole electrical system. People try to work out with what is called as a four-wire system, and this is how it looks like. Okay. So now you see the concept is pretty much similar. Just neglect this lower half for the time being. Okay. So just you have three circuits. Each of the circuit is connected to three different or three individual resistances. They may be equal value, different value, doesn't matter, because previously we didn't had any connection. Now they are getting connected together because of this part. Otherwise, you know that there is no connection. Okay. So basically, there is some current that is generated by this EAN1, which should reach the resistor. That's what is the fundamental idea. Same thing holds good with the second source that has to supply some amount of current to this second resistor. Same thing holds good with the third. Okay, once that particular value of currents are supplied to the load, now I just have to bring the current back, right? There is no hurry, or it doesn't matter how much time it takes or whatever. Okay, so what they did was they try to apply the Kirchhoff's current law, and they try to combine here. Can you see there are nodes now? I have two nodes, right? If at all I have a current flowing here, that is equal to IA. Oh, sorry, I'll write a small letter as per the convention. So there is a current coming here. This is IA. Are you okay with that? There is a current coming here. This is IB. There is a current coming here, which is IC. Now, what is the current that flows here in this line? What is the current? IB. Kirchhoff's Kirchhoff's current law. What is the statement? Right. So at a node, current leaving the node equal to current entering the node. Correct. So can you see there are three currents coming to this node: IA, IB, and IC. Three currents entering, one current going out. So the current leaving this particular node should be equal to, right? Can I write? This is IA plus IB plus IC. All right. So again, you can see that at another node, current entering should be equal to current leaving the node, correct? So whatever IA part coming here will leave along this path. The current that is IB will leave this path. Current IC will leave this path. So you actually don't need three wires. You simply need only one wire. Ultimately, that's all. Okay. Right. So this wire actually brought the concept of neutral lines. All right. So I'll try to write here. Neutral line. All right. So for a four-wired system, if you really take care of all the 3 points that we had written earlier, right? So all the 3 points, right? Peak amplitude should be same. There should be 120-degree phase difference among the three waves you have written, and all the load should be balanced. In the sense, all of them should be same, right? So I'll write one point here. If all three conditions, right, are met, then wonderful thing happens. Okay, they observe that this IA plus IB plus IC, whatever you wrote over there on a neutral line, right? That automatically becomes equal to 0. Okay, what do you mean by that? When IA plus IB plus IC equal to 0, right? It's a sum is equal to 0, correct? Sum equal to 0 is fine for me. I understood. Mathematically, I understood. But physically, what you understand about this line is my question. When I say IA plus IB plus IC equal to 0, physically, you should understand something from that. What is that? Can you try to answer that? There are three currents entering a node. That is, one is IA, one is IB, one is IC. At that
Yeah.
junction or at that node, the sum becomes equal to 0. Why it becomes zero? Because you satisfied all the three conditions that were discussed earlier.
Yeah.
If that is, if you have satisfied, it becomes a zero. It's fine. Mathematically, we are fine. Physically, what you do? Physically, if I have a circuit like this, and when I say there is a line connected, and on that line there is no current, because some of that current is zero. On this neutral line which we have written here, there is
Yeah.
no current.
That
Okay.
means the current leaving it is zero.
Yeah, there is no current. No current is actually flowing on this line. Correct.
Okay.
Is
Yeah.
is are you okay?
Yeah.
Because IA plus IB plus IC 0 means the current which is flowing on that neutral line itself is zero. Correct.
Yeah.
Can I remove the line? When there is no current flowing over there, why do you connect a line? You can remove the
Yeah.
line,
You
right?
can.
Yes. All right. So
Yeah.
this means the neutral line is not required. Correct? It's not, but there is a condition there you need to satisfy, right? The 3 points which we mentioned. Any one is not satisfied, this is not going to be valid. Okay, right? But always, right? We will be moving now ahead to what is called as the three-wire system.
Yeah.
All right. So
Yeah.
three-wire system actually requires no neutral line. That's all. Okay. From the above one, I simply remove what do you call the neutral line. Simply eliminate that. You get your three wire system. Okay. Let me try to face the
So
same.
can you go up once? Can you just show the four-wire diagram?
Yes, 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 definitely. Just check this. Okay. This is the four wire system. Yeah. You are not able to see. Okay. Okay.
Wires here.
The four wires here, three wires are actually taking your signals from these three. The top three lines, what you see, right?
Yeah, those are three
Those
wires.
are the
Then
three
why?
wires, and the another wire is actually this one. This is the fourth wire.
The neutral.
Yeah, the neutral.
Okay. So what about the other ones? The ones like below the.
These you are talking about.
Yeah, don't
They're
those count?
no, they're actually basically just for representation purpose, right? So practically,
Okay.
if you try to build a circuit, right, we will
Yeah.
be assuming something like this. So you have three supplies, three resistors, right? So here itself you connect. This is one. Anyways, for showing purpose, I have to take like this. That's all. Otherwise, it's actually the straight line. So lines
Oh,
are just like that. So here itself you club them all together and bring it. So you see, you don't see those wires coming into picture like this, right? So they are not there.
okay. Yeah.
Okay, so that's how. So the wires which we have considered so far, the wires we call them only when you see some physical existence over there. Okay, otherwise you don't have to call them as wires. All right. So that's why. So this portion, this wherever the IAIB are written over there, consider them to be a part of your load itself. Okay, so they are not separate lines.
Yeah.
Okay, so that's a four-wire system. Hope you're fine with that. Right?
Yeah.
Let me draw the three-wire system once, but later I'll definitely write it once again. But before. Okay, so this is the same four-wire, six-wire system which I have written. Now I will remove completely this. Okay, so I don't need this. I'll remove the neutral names as well.
So for this, is that like reactive power, active power needed?
Uh, it depends upon what type of problem you solve, correct? There may be a requirement of active, reactive power. But in general, three-phase circuit, as per the syllabus I saw, right, what you had shared, it
Yeah.
doesn't require any power calculation. Only the simple power is required, that is calculated using the product of voltage into current, VI.
Oh,
Okay,
okay.
only that part is required. All right.
Yeah.
So now you see, this is the simple three-wire system. So you have three resistances at the end. Connect the ends of resistors to a single point. That's all. You don't need.
Okay.
You cannot consider them as wires. Again, the negative terminals of each of the power supply, each of the voltage source that you have, right? You connect them together. That's all. So
Yeah.
the ultimate thing is, you think so why this is very useful, I'll tell you. Consider that there are three power generators located in a point where we generate power. Maybe it's a hydro thermal plant or any other plant. Okay, so each one of them is a power generator. Okay, so that is EAN1, EBN2, ECN3. All of them are different what do you call power sources, right?
Yeah.
And this, let's say there is a city. The city, if you try to divide them into three equal pieces, right? Because every house is a resistor for power source, which is located say 500 kilometers from here. For that source, my house looks like a impedance, some
Yeah.
Z1. So again, this R does not stand for a single house. It's a group of house or a colony or some area in a city. Just think like that. Okay. So in such cases, if you consider three different regions of a city which are approximately equal resistances, right? They look like equal resistances. And if
Yeah.
you have three different power generating stations located in a particular power source or power plant, you can try to connect them in this fashion. What you save is, you save 500 kilometers of this line. That's what you save ultimately.
Okay.
Correct? You don't need another line which takes the power back, right?
Yeah.
If you do this, the six wire system, right, you need three lines of that same distance, 500 kilometers, 500, 500, right? Totally
Yeah.
500 into 6 is what is expected. But if you try to satisfy a condition, right, then you don't need, you actually you are eliminating three lines, you are saving three lines, the copper or whatever conductor you use, right, you save that much
Yeah.
of conductors, so you save a lot of resources. All right, so
Yeah.
this was the basic idea initially which they started doing research on, and they came till here. So this is the fundamental idea that is behind the concept called three phase. All
Okay.
right. Okay, now we'll draw the three phase currents or voltages. All right, so how they should look like, we'll try to plot. So from there the concept actually begins, right? Okay. Okay, let me right, let me change the color. Okay. All right, so this is where I'm measuring the voltage. Now I need three different voltages. Okay, so there has to be three different voltages. Each voltage should differ by 120 degrees, isn't it?
Yeah.
Okay, so it's easier to start with the normal, what you call as the simple waveform. Okay, so the simple waveform in the sense will be starting with the sine wave. Okay, so it's starting with 0. Let me try to write some points here, which I'm going to use them as a reference. Okay, so 1, 2, this goes to the peak, 0, negative, and 0. Okay, so let me draw a few of the points like this. So let me, This is the peak value. Okay.
Yeah.
Starts from 0, goes to a peak, comes down, reaches a negative peak, crosses this, reaches the peak on the other side, and flows like this. Let's say. Okay, this is first wave. Right, now what we do, the remaining parts, right, I'll try to draw two more markings. One, I'll draw, say, X, and one more point I'll draw. I'll divide the remaining pieces into two equal pieces, okay? So one X over there and one dot, one something like a circle. I'll try to do this. I repeat this everywhere. So this is X, this is it is, this is X, the one, there is X, one. So have a dot here. There is an X here. Okay. Now what I'm doing here, in the next part, I'll try to repeat what is happening here with respect to the X mark which is written over there. Okay. So for this X mark, right, I'll try to draw a, okay, let me change the color. So this is going to reach a minimum here. So it's a 0 here. So this is how it comes. It touches here. Okay. I'm trying to connect this, the one corresponding to these point. Okay, so it actually is a minimum here. It goes to this point. It should reach a maximum peak value here. So it reaches a peak here. Then it comes to the 0 here. Okay, then it becomes once again negative maximum here, and so on.
So what is the red?
Red is the other one which has 120-degree phase difference compared to the black colored one.
Okay.
Correct.
Yeah.
So I have to draw how many waveforms? 3 total. Correct.
Yeah, one for 0 also.
Yeah. So this is the second. Okay. It can be, if I say the first one I have drawn is EAN, this the second one I'm drawing is EBN.
Yeah.
Okay. I need to draw a third one. Let me change the color, and the third one should be, so corresponding to this, right, the dotted line. It actually has to come to the lowest or the maximum point. Okay, that's corresponding to this. So let me say I'm plotting here. So this is a minimum point that corresponding to this dotted, the circle which I have plotted, right? So this is how it looks like. So it goes here, reaches a maximum here, okay, corresponding to this dot. And for the next dot, it should reach 0 and it should flow in the same way. Okay, so it comes to a minimum. All right, so this, okay, let me do a change so that I will be able to show you the 120 degrees also properly. Okay, if I draw like this, 120 degrees not visible. I'll show you. I'll do the opposite. What happens? I'll make it to reach maximum here so that I'll be able to show you the 120-degree phase as well.
So, but at 0, it will just always be 0.
No, it's not 0, right? Because you have to have a phase, right?
Okay, just
Different
angle is
phase.
0.
Yeah. Okay. So now you see this comes like this. This comes to 0 here, reaches a negative, and it goes like this. I'll try to make it correct. So it starts from here. It passes through 0. It comes to this, and like this. Okay. Now measure the angles. Okay. So for this one, for the black colored one, I'll say the phase angle is 0 degree. Are you okay? Because it starts with 0. At 0, it is 0.
Yeah,
For this one, what is the phase angle?
it's starting at pi by 2.
It's not starting at pi by.
Oh,
It's below, right? So the blue color is below. How do you find out the
okay.
phase? I'll tell you an easier method. So look at what is happening. It is crossing 0 and going to the positive. Correct? The first one.
Yeah.
There I measured its angle. Correct? Now you see
Yeah.
where the blue colored one crosses 0 and goes to the positive. That's happening over here.
Oh, okay.
Right? Corresponding to that, whatever is the angle, That is the phase angle of this. So this is
So is
0,
it 3 pi by 2?
this is 90, right? This I am dividing into 3 pieces. So each point is 30, 30, 60, 90, 120. So this is 120 degree. This is what I want, right?
Yeah.
120 phase shift. Correct. Go ahead. So this is 120, 150, 180, 210. How much is this? This should be
270.
240.
Oh, yeah.
240, right?
Yeah.
So angle between each of them is 120, which is satisfied.
Yeah.
Right? So this is the voltage waveform. Right? So three different voltages have been plotted here. So I'll give the names accordingly. So this is, maybe this is VBN for us. The black colored one, I'll write VAN for us. And
So what does the N mean there?
N is a neutral point. Okay.
Okay.
So this is VCN. You don't have to write an N there, because there is, anyway, in this system, there is no N at all, right? I don't have a
Yeah.
neutral line. So simply you can write VA, VB, VC, or EA, EB, EC. That's also fine.
Yeah.
Since we followed something like that, N1, N2, N3, I wrote it like that. Okay. So even in a three wire system, you don't have to write this N1, N2, because there is no separate N1, N2, right? All are same.
Yeah.
So I'll update. Okay. I'll just update them simply as N itself. So you see, this itself is the N point. This itself is a neutral point.
Yeah.
So everything is measured with respect to N. So you can give a name as EAN, EBN, ECN.
Yeah.
That's all. Are you okay?
Yes. Can I just go to the washroom?
Yeah. We'll take a quick 10 minutes break and we'll continue. All right?
Okay. Sir.
Sure. So this is how we draw the waveform of voltages. So if you want to draw the currents, you will draw same thing, but just change the names like IA, IB, IC. Instead of VAN, you can just call here, this is IA, this is IB, this is IC, because they are in the same phase, right? So voltage and current are same, because we know that we are having the resistance over, right? So I'll just try to draw one point here. Let me try to draw like this, right? For current waveforms, right? We just have to change the actually the amplitudes. That's all. Amplitudes will be calculated as per this. One is EAN divided by R. That will be equal to EBN, that is divided by R. That is also equal to ECN divided by R. Amplitude. This is amplitude, magnitude of your current waveform, right? So because it's a voltage divided by resistance, right? So resistances are same. So I'll be drawing the same thing, but this magnitude is going to be different now. That's all. Magnitude's value you might have to change, like EAN by R. That's all. Okay. All right. So coming back to the okay, let's try to draw a general three-wire, three-phase system. It's the same thing like what we actually had drawn, right? I'm just pasting that once again. Okay, so this is where the three-phase concepts begin. I think I have the same thing available. And I'll make the changes as per the requirement, and my requirement is just like this. So okay, let me make changes, and I don't, just a second. It's okay. So what I want is, I don't want anything below this. Let's say I don't want this. Okay, I want to connect all of them together, because I know that there is no neutral line, and I don't have to make any other connections below this. So simply you can remove that, and simply you can connect them. So connect them. This is the first one, and connect the others in this fashion. So if I do so, right, this itself is what is my, uh, I can call this is a neutral point, right? And there is no n1, n2, etc. So as usual, right, we understand that I just have to write n1, no n1, n2, etc. Simply you can write n itself. So this is cn, bn, an. Okay, so this is a simple representation of the three-phase three-wire system, and yes, we can write in any of the formats. You can try to write its a phasor representation. Previously, I told okay, we'll be writing something in horizontal, but it's not required. You can try to write something like this. This is EAN. Just give an angle of 120 degree between the other one. That's all. Okay, so that becomes EBN, and write one more, right, making the condition, satisfying the condition of 120 degree, that becomes ECN, right? Yeah, condition is that this angle should be 120. That's all. How you write, which direction you write doesn't matter. Okay, from where you start actually has nothing to do with it. So I can draw another one like this. This also is fine. Okay, so I can write IA here. 120 degree should be between this and IB, right? There should be 120 degree between this and IC. So that implies that this angle is also 120. That's all. So you can write anyway, anything is going to be fine for us. E is actually, so you see, we have various notations possible for voltage, right? Either it is preferred to give E or small letter v, anything you can give. Okay, E means a voltage, small v is also voltage, right? But current, we don't have many symbols like this. Current uses only I. Okay, so it's a convention. It's a convention that for DC power supplies, DC current, DC voltage, right? I use capital letter. So capital I says that my current which I'm talking is a direct current. Okay, if I write capital V, it means, right, the voltage which I'm talking is direct voltage. Okay, it's a DC voltage. But if you see similarly write small I, small v, indicate that what I'm talking is about the AC. It's a convention, right? So it's easy for otherwise every time you mention uh, the current is DC and something like that, you need to write everything like that, right? So just to avoid that, people follow this convention in electrical and electronics. Is that okay? Sure. All right, so let's move further. So this is how the three-phase system comes into picture, and this is called as the three-phase system. Normally, we don't have to mention that three-wire. The word three-wire will not come into picture any further. Simply, we call it as a three-phase system. Okay, but three-phase means this one. It should be something similar to this. Okay, there will be three power supplies, three loads, and three wires connecting each other. Right. Okay. Now, though we didn't consider any specific type of connection between the sources or loads so far, we basically have two main type of connections that are possible, right? Whenever we consider a three-phase system. Okay. So the first type of connection that we are going to see is called as a star, right? It's a star, or it's a Y connection, WYE. Okay. This is one type of connection. Yes, as you told, the next connection that we'll be seeing is called as a delta connection. Okay, so right. So the star or the Y connection is something like this. If at all I want to make a connection of this type, right, I should be making the following type of circuit. So I need three power supplies. So the three power supplies are now not connected as we considered earlier. We'll be connecting in the following fashion. Okay, so one here. Let me consider the second one over here, and let me draw the third one over here. Let's see. Okay, these are the three different power supplies, voltage sources. There is one common point because all of them should be connected to one common point, correct? That's the neutral point. So you will make the connection like this. So take the negative terminals of all the batteries or the power supply, AC supplies, to that point, one common point, whichever you consider, you take it, you connect it to that. Okay. The other points, whatever we have, we are supposed to connect them to the loads, right? So connect the loads also in the similar fashion. So this is load number one. Okay, I'll try to draw load number. I'll try to draw the load number 2 here. Okay, so let me draw it in. So this is the load number 2. And I'll draw a load number 3 over here. So from these loads also, I have to take a common connection and I have to make the connection to touch a common point, right? So that's my basic requirement as we have seen earlier in a three-phase, general three-phase system. So the same thing we are trying to do now. So though we have several, like the basic two types of connections possible, the analysis will help us in understanding the relationship between various types of currents and voltage. Okay, so this is the first one. I'm connecting this. This is one connection. You can see that from that particular power supply, it's coming to this. So if I draw here, plus minus VAN, this being my neutral point. So this will be the IE. Okay. And similarly, I will try to write another connection. That is, let's say from here, I take this and I'll connect to this. Okay, so if I say that this is plus minus VBN, this will be the current, that is IB. Okay, similarly, I will be having another connection over here. So there is no connection between that point and this. So I'll show it in this way. Okay, between the two wires, we don't have a connection, but still the current IC flows here. Okay, so this is plus minus VCN. Okay, this is all are small letters as our notations. This should be the small letters, okay, because they are AC. It's V. Right. So this is one type of connection. Now we need to talk about various quantities, right, that are related to this kind of connection. Okay, so to understand the various quantities of this, I'll just consider only one part because both are same. If you see carefully, right, whether you connect this part or this part, both are the same connection, the star connection, correct? The sources as well as the loads are connected in the same format. So just to understand the various terminologies we are going to use, right, I don't need both of them. I need only one of them. So let me just try to write the the loads only. I'll try to draw the loads. Okay, so only the load part I'll try to draw. Okay, so this is the load. Okay, now let's consider the lines like this. considering that to be the common point. Yeah, each of them will directly go to the source. Okay, I'm not showing the source part now, right? So this is one line, this is the other line, and let me move further. This is the third line. Okay, we have the three lines that are over here. Okay, let me give some names for our reference. So the one which actually flows here. Okay, let me give a name in this fashion. So this is the point A from which the current or the voltage is applied. This is also A itself. Okay, it's the same point. I have a C, say I can write B here. This is also the B from which the current is coming. This is the C point, and I'll say this is the C. Okay, now I can say that this is a neutral point, right? Okay, now you see, uh, wherever you actually connect a load, correct, right? You see, this is a resistor or impedance that is present over there. What we can do here, this is what is called as a phase component. It's a phase component. Okay. Similarly, this is called as a line. Okay. So similarly, now I understand that this is a line. That's not a phase. Phase is this. There is a component, phase component here, and the line along which you are supplying the voltage or current is called as a line component. Okay, so this is line A, this is line C, and I have line B here. On a line B, whenever you see a resistor impedance that is present over there, you will call that as a phase. Okay, that's a phase component. Right? So this is also the phase component itself. Now let me try to write the normal convention. So you see here, if I write E, A N, E, uh, B N, and E C N here, right? Just look at this. EAN is the voltage between A and neutral. Is it okay? A point is here, neutral is here. So between them, if you measure a voltage, that is a phase voltage. Are you okay? Because the name, as a name given, it's a phase component. Any voltage that is measured across the phase component is a phase voltage. Are you okay? So that's why EAN, EBN, ECN, they will be the phase voltages. Okay. Now you see, I'll define different voltages now. If I measure the voltage between the points A and B, okay, point A and B, you are trying to measure the voltage between two different lines, not the phase. Correct? Are you okay? So that means there are three more quantities that you will be able to measure in this kind of connection, that is E, AB, E, BC, E, CA. Correct? Between the line AB, it is EAB. Between the lines B and C, EBC. Between the lines AC or CA, it's ECA. Okay? They are the line voltages. Is it fine? Do you have any doubt? No, right? Oh, fantastic. So this is the first type of connection. Anyway, we'll try to we'll be discussing in detail about what you call as the star connection soon. But before that, let's try to define what is called as the other connection, that is called as the delta connection. The next set of connection normally people use is called as a delta. All right. Again, just to understand the various terminologies, we'll directly write the delta. I will not write the circuit like this. Okay, so anyway, it's understood that how to make the connection for delta. It becomes easy if I draw the delta connection once. So what I do, uh, not possible. All right, let me use the same thing. So for a delta connection, so we need the three different loads to be connected to form a triangular structure or a delta structure. Okay, so this is the first one. Let's see, and let me assume that there is another line. Yeah, they will also remain same. Okay, same connection. Whatever you draw here on the other side also, you will be connecting the same. So, okay. Anyway, right now I'll not draw that. Just let's save some time. Okay, it's understood now. Okay, so let's take the common points now like this. So each of the load or the source, right? Two ends of, right? Two different loads or sources are connected to a common. This is how the delta structure is created. Now there is no neutral point here. Okay. Right. Now let me make the connections. This is the first one. All right. And this is the second one. And this is the third one. Okay, let's give some names. So this is the point A, point B, point C. All right. Now A, this is a line, and this line is going to carry a current. Let me write IA. So this is IB. This is IC. Okay. Now, so that means this is the point B, this is the point A, this is the point C, right? So what happens here is the current which is going to come from A, you can again, this is actually a convention. So I can mark something like IAB, A to B. Okay. Here some current is assumed, that is I B to C. And here some current is assumed, this is I C to A. Okay. Now you see all the sum should be equal, actually should be equal to 0. That's what happens here. You see no line carries current back from these loads to the source. Correct? We have three lines coming in. That's all. You don't have a current that is going back. So it's actually called as a virtual ground concept. Virtually you can see that there is some neutral line that is having, but you don't see that. Okay. So no physical neutral line can be identified like neutral point can be identified like the star connection. But the sum, ultimately the sum IAB, IBC, ICA, if you take all sum together, it ultimately becomes equal to 0. Okay, fine. Now, very similar to the line and the phase components you saw here, right? Very similar to that, we have we can try to mark some of the voltages and currents over here. Okay, so let me try to draw here. If I say IA, IB, and IC are the three different currents that I want to give some name, what do you call them? Are they line? They are line currents. Are you okay? Because they are the currents measured along the lines. Line A, you see, this is a line. Okay, this is a line. This is a line. So I am measuring those currents on line, not a phase. What is a phase? So yeah, so if you have a something which is measured on a phase component, then that will be a phase quantity, correct? So now, as you told, I'll write IAB, IBC, ICA. What are they now? They are the phase. They are the phase currents. Okay, fine. All right. Right. Now we'll do the proper analysis of each of the various type of circuits. All right. So we'll do the analysis of a star network or star connection. So here basically we have first part is over. That is actually the introduction part and what are the various types of components. Now we have to analyze the star circuits properly to relate the what you call the relationship between the currents and voltage in a star type of connection. That's the first component, first thing that will come now. And after that we have the analysis of a delta circuit. Again, over there, we'll try to relate various types of currents and voltages that are present over there, right? That's another derivation. Then we'll try to derive the equation for measurement of the power. How do you measure a power in a circuit? And then there is one practical circuit which actually using power measurement using watt meters. Okay, so those are the concepts that are there. Only those concepts. Maybe one more. If we get another 2 hour session, everything will be completed. I guess. Okay. Within that, I can come. Sure. So let's start with the. At least let's try to draw the circuit for the day. Maybe it will take some time, but let's try. Okay, I have something readily available. I'll take this itself. Okay, then I'll modify. Okay, so let's start giving the names as per our convention that we had followed so far. So let me. Okay, so this is what I call as line A. The second one is line B. This is what I call line C, and I'll mark this is A. This is B. This is C. And we already have marked some currents. Let's follow the same thing. This is IA, and the current that flows here is IB, and the current that flows here is what I mark as IC. And we need to measure the various voltages. So here I measure one voltage. That's what I'm going to call it as VAB. I measure another current over here. So this is VBC, and between the lines A and C, I should measure a third voltage. Okay, so this is VCA, correct? C and A. So yeah, they're not phase quantities, they are the line quantities, correct? Between the lines I am measuring. And as you told, I need to measure the what you call the phase quantities as well. Let me assume that there are equal resistances that are located over there. And I have, say this is plus minus. You see the voltage is I am measuring between A and neutral, correct? So here I am measuring the voltage plus minus. This is V, B and neutral. Here I am measuring between V, C and neutral. So the currents that flow, that actually flows here, I'll try to mark according to this. It's a phase quantity, so I can try to write it as IA neutral. This is I, B and neutral. This is I, C and neutral. Okay. All right. So these are the various quantities which we actually have discussed as phase voltages, line voltages, phase currents, and line current. Phase currents and line currents. Everything we marked for this given circuit. Is it okay? All right. So let me try to write something below this. So with respect to this circuit, so you need to consider a star connection with three equal resistances of value R are used. So just I wrote everything in one sentence. Right. Now let me try to write some common notation here. So let, you see there is VAN, VBN and VCN. What are they? I'll show you the correct. Yeah. So it's a, each one is a phase voltage, correct? Since our power supply everything is unique, right? Everything is the same, right? I can give a same notation for them. I'll call them VAN, VBN, VCN. I'll give a single notation VPH. All the three can be called as VPH, phase voltage, right? No, each individual one. VAN is VPH, VBN is also VPH, VCN is also VPH. Not a sum, not sum. Okay, individually. I can instead of writing VAN, VBN, VCN separately, I call them, right, as VPH. Individually, they are VPHs, right? Because they are same, right? I can give a same notation, single notation for all of them. Similarly, VAB, okay, VBC, and VCA. What are they? They are the voltages measured between the lines. So they are the line voltages, correct? So I'll call them as VL, simple notation, right? VAB is VL, VBC is VL, VCAI is also VL. Similarly, let's write IAN, IBN, and ICN, right? Phase currents. Yes, so we will call it as yeah, IPH. Okay, and I also have IA, IB, IC, line current, correct? So I will call this is IL. Is it okay? Okay, now let's go back to the circuit. You can take any one part of your circuit and you can try to apply what is called as a Kirchhoff's voltage law. I'll mark a path. You can take any other part of the circuit as well, but I you can try to write this. So just try to understand what I'm trying to do. So for application of the Kirchhoff's voltage law, I need a closed path. So let me take a closed path. I'm trying to write AB. So AB means, sorry, not this path, my mistake. I'll go back. So for VAB, I'll take this path. Okay, I'll move around my circuit in this particular marked direction. I start from A, move around the circuit in this following loop fashion, and I reach B. Is it okay? Right. In this path, if I move, I want you to tell me an equation for VAB. Okay, VAB is the voltage between A and B. So I want you to tell me what is VAB. VAB equal to, apply Kirchhoff's voltage law, and you have to tell me. So when you VAN, okay, whatever voltages you get around that circuit, you have to consider. Okay, so it's actually you take a complete loop in the sense. It's like this. Okay, yeah. What you told? Can you repeat? VAB equal to VAN minus VBN, right? Perfect. Yes. So VAN is equal to, sorry, VAB is equal to VAN minus VBN, right? Yes. So that's the one which I require. You can apply this for other loops that are present in this circuit as well. Okay. Any one is sufficient. So let's stick to this itself. Okay. So I can write. Okay. Uh, from the circuit using Kirchhoff's voltage law, I can directly write what you said. That is VAB is equal to VAN minus VBN. Perfect. Because your equation will be VAB minus VAN plus VBN equal to 0. If you want the proper, what do you call, proper Kirchhoff's law, then this is the equation, whatever I have written on the right side, right? But anyway, so you move the AN and BN to the other side, this is what you get. All right. Okay, now let's draw the phasor diagram for this. Drawing the phasor diagram. So let me say this is VAN. This is the other one, and say this is the third one. Okay, angle, I'm taking care of that. Let's assume that I have drawn it very properly, taking care of the angle requirement. So let me give the names. This is VAN. This is what I call as VBN. This is VCN. Now, according to this above equation, if you want to calculate VAB, you have to subtract VBN from VAN, isn't it? So, okay, I think I need some more space. So I'll just move this up. Let me see. I think I still need more space. What I do, I'll copy this down. Okay, so let me mark the minus VBN now. So minus VBN will be opposite direction. Is it okay? Can I say this is my minus VBN? This is minus VBN. Now I need, sorry. Okay, so this till here it's fine, right? Till this equation. Okay, now you see, so VAN, VBN, VCN are what? The voltages that are present in a three-phase network. Correct. How should be they? How? What is the relationship between them? They should be 120 degrees apart. So can you see 120 degrees apart? Okay, so that's also fine. So now your doubt is how do you get the minus VBN? Is it minus VBN in the sense if you look at the vector, if this is vector A, this is vector minus E, correct? Because its direction is opposite. Now you apply the same thing to the VBN. VBN is actually marking downwards, right? So if you see this, see this is VBN. Opposite direction, same magnitude. Its length should be same, but opposite direction is minus VBN. Are you okay? Right. So now what is my intention? I just have to take care of this equation. That's all. Its equation says that if you have VAN, if you have VBN, take a difference. Whatever you get as an answer is a VAB. Right? So I'm trying to implement that here. So VAN is here, minus VBN is here. How do you add two different vectors? What's the rule called? You can complete the parallelogram. Correct? Right? Do you remember? You just have to complete the parallelogram. So complete the parallelogram now. So this is the complete parallelogram. Are you okay? I completed the parallelogram. So the diagonal of this parallelogram is the result, right? So I will draw that diagonal now, say like this. Are you okay? Right? Now let us try to measure the angles here. So can you tell me how much will be this angle? The angle that I'm marking here. Sorry, 45? Are you sure? Can you justify it is 45? How it is 45? VAN, VBN, VCN is 120. No, you see, this is, I'll draw. So this is 120, this is 120, this is 120. So when you draw minus VBN, that actually bisects your total angle. So that should be 60, correct? Isn't it? So this is 60, right? If that is 60, I'm still once again bisecting that, correct? It's 30 degree, perfect. So now you know that this is 30 degree. So other side is also 30 degree because anyway, they have to be same, right? If I draw a perpendicular here, you understand that this is 90 degree, this is also 90 degree, correct? Okay. Now I want to measure this total distance. So this is VAB. If you are fine, can I write VAB here? That is the blue line what you see here, right? This blue line is VAB. That's the diagonal which is the result. That is VAB which I have marked. Now let me split this diagonal into two pieces, right? Because I don't know the total length. One part I call X, other part I call Y. Are you okay? One is X, the top half, the bottom half I'm going to call it as a this. Okay, so let's do the calculation. It's very simple, very straightforward. So if you want to calculate VAB, right, this VAB is equal to simply it is X plus Y, isn't it? what is x? X is equal to, if I want to measure this x is the horizontal component and the angle is 30 degree. Can I call it as what is this? This is VBN. Can I call it as it's a VPH? This is a VPH. The red arrow, and this is another VPH. Correct? Because this VAN I can simply replace it as VPH, right? So not by 2. It is VPH cos 30. Because I want to measure the horizontal distance, it's a cosine ratio. Vertical will be sine ratio, correct? Sine and cos, right? So x is nothing but this is a VPH cos 30 degree plus what is y? Once again, you see 30 degree and I want a horizontal component, means that is once again the cos ratio. Okay, so I'll write 2 steps, okay, so that you don't miss anything, right? I'll write it again. So let me try to write it in this way. This is equal to x I want to measure. So x in the sense this is VBN cos 30 plus this is VAN cos 30. Okay, VBN is a VPH cos 30 plus VAN is again VPH cos 30. So ultimately this is 2 times VPH. What is cos 30? Cos 30 is root 3 by 2. 2 cancels. So VAB is equal to root 3 times VPH. What is VAB? That is a VL. Isn't it? Line voltage is equal to root 3 times phase voltage. Is a relationship between line voltage and the phase voltage in a star network. Okay, and one part is over. Look at the second part. It's very straightforward. You don't have to prove anything. Whatever current is marked as a line current, it itself flows as a phase current. Correct? Same current. There is no change. Nothing getting added, nothing getting subtracted, no change. Are you okay? So next part is very straightforward. You simply have to write one sentence over here saying that, right? Okay. IL line current is equal to I phase current for star connections. That's all. So one you need to prove the relationship between the line voltage and the phase voltage. That's a proof. You need to prove it. For the second part, no proof because it can be directly observed from the given graph. Okay, very straightforward. So we have covered the first part of the analysis. That was the analysis of a star network in this particular class.